U1 action. Hodge string is something like what people are calling BV infinity reduction to cohomology. And there is an interesting relation between them. So it will be the first subtopic of today's discussion. And then I'll discuss the same issue from the point of view of moduli spaces. So it's similarly like we can discuss induction on cohomologies of on cohomology of infinity structures using both moduli spaces and homological algebra. Formulas are the same. So let me first explain commutativity. As follows. Imagine you imagine that you have something like bicomplex. Something like bicomplex. I mean that this means that q square equal to 0, and also q m1 plus m1 square equals to 0. So I will call this generalized bicomplex. Let me explain in which sense generalized. In bicomplex, we assume that this term is 0. Okay? However, it is better to keep this term. And we will see that we would need exactly this definition. Because this formula has a deeper homological meaning. It means that it says that M1 is differential up to Q exact terms. M square, M1 square is homological 0. Okay. We also know these equations as as a version of Maurer-Cartan equation, of course, a version of. Okay. Now, imagine that we have this. Then we will have induction of M1 to cohomology of Q. So to give explicit formula, it's better to pick up homotopy. And we call homotopy H. And write down formulas. So nowadays everybody is writing these formulas. I'm just looking through papers and people like these diagrams a lot. So like 30 years ago they were kind of rare. And it is, so we know it as Kadeshvili formulas. So Kadeshvili is, I hope he is alive, is a mathematician from Georgia. If you know where Georgia is, so it's a small country near Turkey. If you see Turkey from that side, very old, like a very old civilization, like 4,000 years. And Kadeshvili started the school of homological algebra. So it's another reason to stress his name, okay? Georgia, not Georgia in the United States, Georgia in Europe. You see, I have these formulas upstairs. So people call these fish diagrams because they look like fishes. So I still have it upstairs. Okay. We have this operation plus this operation. So it is M1 induced. We can look at what happens in the following way. can consider this equation as perturbative problem in finding M1. So we may say that M1 is M1 1t plus M1 2t squared plus etc. Then we will have Q of M1 1 equals to 0. Q of M1 2 equals to M1 1 squared, etc. You see, I'm looking at this, not a problem, at this setting as a problem of deformation of Q. And here we are coming to what is called Torelli problem. Have you heard this name, Torelli?
Yes, of course.
In homological algebra. So Torelli studied this in the theory of deformation of complex structures. However, we can easily generalize. 1 second. Okay, I'm almost back. Okay. So this problem is known that sometimes it has abstraction, and abstraction, of course, is the class of M1 square. Okay. So after I reminded you this setting, let us come to the issue that we study, namely, just imagine that we have a U1 action everywhere in the business. And we understand that if you have U1 action, you have two things. First, you have the contraction with the U1 vector, and that's basically the only thing that you need. So the operator of contraction with U1 vector, people call it differently. Some people call it BV, but since I'm coming from the mathematical physics camp, I'll call it G minus. So the name G minus is because here you show that it comes from the U1 action. It's in the name. So when physicists are writing T equals QG, they say that you have topological theory. So Q is a differential. So it's for a general energy momentum tensor, all components, and also both left and right. So originally, people introduced T0 that corresponded to Z d over dz, and correspondingly is G0. There was also T0 bar that corresponded to anti-holomorphic piece. Now we see that U1 rotation is a difference here. So U1 rotation corresponds to G naught minus G naught bar. But it's too long to write it this way. So you say simply, first you say simply G naught minus, but it's also too long. So you say that it is G minus. From considerations of two-dimensional topological theory, it turns out that the deformation that we will try to write down is G naught minus, is G minus exact. So that's what people want to study. Okay? So this is homological Torelli. To show that this is homological Torelli, I need to show how Torelli is embedded in homological Torelli, right? So by Torelli, people mean something like this. D bar plus D mu, where mu is Beltrami. So all Torelli problem was the problem of finding such Beltrami differential that this thing squares to zero. So this is Torelli problem. D bar plus mu d squares to zero. So now D bar is replaced by Q. You see here we just show that Dalbo is nothing but a differential. So in homological algebra there are many resolvents, and Dalbo is just one of the resolvents. So here we show this. Now here we see G minus. So it's another differential. Of course, G minus squares to zero. It is realized as holomorphic Dalbo in geometrical setting. And here phi and here phi is Beltrami differential. So when Torelli was studying this, and when people were studying this Torelli problem, they had no idea that Beltrami differential is actually just an element of polyvector fields taking values in zero star forms once again, right? Now we are aware of this fact, but in old days they were not aware of this fact. So that's how it goes. So and this is an abstract setting, and this is so-called complex geometry setting. So when we study Torelli problem, we have the following equation. So let us square. Okay, like this. So what we have here is the homological Cadeiro-Spencer. So actually, Cadeiro-Spencer would happen if you take G minus, if you take G minus out of it. So actually, Cadeiro-Spencer is Q phi. And you see, so here we have, so you can take G minus in different ways out of it. Now, now there is an issue how to study abstractions here, because we know that Torelli problem sometimes has negative solution, sometimes has positive solution. So people are supposed to study abstractions, and it is clear how to get abstractions. You are getting abstractions when you first take phi in cohomology, phi 1, I call this. And then you compute this operation. And when you compute this operation, you can have an abstraction, right? And then what can you do? So in the simplest case, namely the case of QG this phi is just a function. So here, so this thing is exactly zero. So it's there is no problem at all. However, if you study higher things, you can have abstractions. However, as you know, there is, I think it's called Todorov theorem. So Todorov theorem says that there is no obstruction on Calabi-Yau manifold. Do you know this theorem?
Oh yes, of course, I'm aware of it.
Okay, so, but Todorov theorem also has homological generalization. So Todorov actually made a geometrical theorem. Explanation why Todorov theorem works comes from two facts. First fact is the Hodge decomposition of cohomology. And second is what Kyoja would be happy to hear, primitive form, or actually polyvector fields, differential forms, correspondence, not correspondence, identification. So if you have this, you can prove that there is no obstruction. So it is surprising that Todorov theorem was proved at 80s when people already knew homological algebra, but Todorov still formulated it in terms of differential geometry. Surprisingly, so it was after Kadeshvili theorems. So people did not see similarity between two things. So it turns out that first people prove something in differential geometrical context, and only later they have homological generalization. However, things should go opposite way, in the opposite way. First, you should have homological understanding, and only then geometrical example. So, but still we are too silly. You see, we are still going this way, from experiments to theory, from geometry to homological algebra. So we should better go opposite way, you see. Consider geometry as an example and not as a source of inspiration. And so what is homological Todorov? Okay. You see, unfortunately, people are not even writing these words like homological Torelli, homological Todorov, etc. So I am using these terms. People are not using them for some reason that is completely unclear for me. So this is not a standard notion, homological Todorov. That's how I call it.
I'm fine with that.
So I am following Kontsevich, who said homological mirror. Okay, so, but see, it's because if theorem is a representation of the general construction homological algebra, you should call corresponding homological theorem homological something, right? So homological Todorov theorem says the following thing. Suppose you have a commutative. So when I say commutative, I of course mean supercommutative. Okay. A ring. Second order operator. I don't know how should I call it? I'll call it P. So P, first of all, because one example are polynomials. Also P because it's a polyvector. So if you, I have to invent a name. Second order operator. Oh, this would be G minus. And of course I forget the first order Q. First order operator. Commuting with G minus. So is it clear what I mean by the second order operator? Do I need to explain what does it mean? Oh, operator, of course, on P. Is it clear what does it mean in general?
Yes.
So
For example, that should be the BV Laplacians, right?
but it's an example.
Yes. Just
but in general, second order differential operator is such that its commutation with the multiplication is the first order operator.
Does it have to square to 0 or not?
Yes, here it has to square to 0.
Okay.
Of course. So your question is proper. You may ask, what if it squares not to 0 but to Q of something? So of course this theorem would have or should have further homological generalizations, but I want to make first generalization. Okay, that is I am trying to make generalization that is relevant, that I think is relevant to what I am discussing. However, you will see that what I will give from homological algebra would be the level 1 understanding of special coordinates. It will be homological, but it will be level 1. The higher level of understanding would be if you will use what I'll call, I am not a collaborator, but all of them are my friends. So Хороshkin, Markaryan, Shadri. Approach. So there is a viewpoint on what is going on that is deeper than what I am explaining. Okay? But you see, I'm not among these people. And They always criticized me for being old-fashioned, but still I want this old-fashioned story first, okay? And also because for me it is hard to understand the modern viewpoint before you understand the old-fashioned. You see, it's like before you understand homological Todorov or homological Kadeira Spencer, you should start with Kadeira Spencer, right? And then you understand its homological meaning. So similarly, here it's better to start with the Hodge strings. So I hope that one day I would be able to explain it on this level. Okay. So after making this disclaimer, I'll continue. Okay. So suppose you have all this. Then we can formulate Tarelli problem. Not only formulate, but also solve. Okay? In solving Tarelli problem, we will do better than we may expect. We will not only prove the solution, we would also give a distinguished representative. You see? So you know there is a difference when you prove that solution exists or when you give explicit formula for the solution. Yes. So second is much better. And this solution would be exactly Todorov solution. Okay. But first we need to formulate problem in this setting. So here is multiplication operation, yes? I call it M2. So we would like to study deformation theory. So here I understand phi as operator pi to pi. So it's here phi is understood here as an operator acting from pi to pi, from poly to poly, okay, from ring to ring. So actually, how can you solve this problem? So let me give several steps. So phi is phi1 plus t squared phi2 plus etc. Okay. Q g minus phi1 equals to 0. Okay, so here what we say, that phi1, so let us say it belongs to cohomology of Q, and I will call it this way, Qg minus. So let me introduce this notion. So what does this mean? If there is a Hodge decomposition, then the space P is decomposed into this sum. What P0, okay, let me call it P1. So Q on P1 is 0, G minus on P1 is 0. Okay? Cohomology. And P4 is a free Q and G minus module. Okay?
Sorry, but I can see the bottom of the board because
I saw it. So P4 is a free Q and G minus module. So P4 is a span actually, because the algebra of Q and G minus has different representations. So there are trivial representations like P1. P4 is a free representation. In general, we can have more complicated representation. But we assume that only these representations are present. And this is equivalent to complex Hodge. Do you understand this? It's equivalent to complex Hodge.
yes, in the geometric examples, it sounds like when you choose the representative of the Q cohomology, the phi1, you require, of course, it should be Dolbeault closed, and you further require it is also holomorphic Dolbeault closed. Is that how you choose
So
this?
let us clarify. So you say how it is realized.
Yes, in the geometric example.
Yes, but you may see that actually what you need is this.
Yes, yeah, I see.
So once again, here I don't want to have anything like orthogonal decomposition. So there is a decomposition in direct sum, of course. So I'd like to consider Hodge as complex Hodge as a condition on the representations of the G minus algebra that are involved. And it is clear that there are other representations. And what Kyoji Saito described is that there are other representations. So, okay, gravitational descendants happen when you have other representations. That you can, and existence of so-called gravitational descendants is just show to which sense they somehow measure existence of other representations, or you may say the following way. There is Briscoe lattice, okay? And so in the Briscoe lattice, you have the Z spectral parameter that is acting. So if spectral parameter is acting by 0, it means Hodge. I'm sorry, I need to have a several minutes break because I need to change the cigarette. And it's hard to talk without nicotine for me, okay?
Okay. So then how many minutes do you need?
Just 2 or 3 minutes. I'll try to
2 or
find
3
something.
minutes, okay. I resume the recording so we can continue.
Okay, very good. So, we want, so here we have this condition, and this condition on Pauli vectors so when I say that we have this condition on Pauli vectors, I assume that a geometrical example, this is the condition actually coming from polyvector differential form decomposition, identification, using the top form, and in geometrical case, it is proven by standard technology of Hodge. Okay, so we assume this. Now, what can we say about phi 2? I'm sorry for sitting. It's because, as you know, I'm a bit tired. That's why I'm sitting. Okay? So I think that we need to solve the following equation. Q on phi 2 and here we have this operation. Now we need to understand why this equation is solvable. So here I need to make a comment. because there are two senses in which phi1 is understood. I mentioned it, but this formula is ambiguous. Phi1 may be understood as a vector space where we have the action of operators, and also phi1 may be understood as an operator. Of course, here it is understood as an operator. Okay, so if I would not be that lazy, I would say that here I actually want to say M2 phi. Okay. Maybe it's a bit better notation. So what is written here? Let me draw a picture. You see, when you start to work with these M2s, it's better to draw pictures. So here you have phi1, and here we have phi1. And what you have here, and here is M2. And what you have here is G minus. So this is actually what you need to solve. Okay, so now let us get it straight. So, okay, let me write it in a more convenient way. So, 1 second. So how do we understand this? We understand this in the following way. You have M2, you have phi sitting here, you have an operator. And you have G minus. So, commutator. So when you have G minus, you note that G minus is not a first order operator. Rather, it's a second order operator. You see, I'm still discussing this picture. Maybe it's better if I'll start by writing kind of an answer, and then we will discuss why this answer is correct. Phi1, M2, So first, I'm sorry. First, I try to explain what we are struggling with. We need to compute the square of this element. Okay. So how can we draw it? So here is the action of G minus. I'm sorry. You see, I forgot this computation and graphs for a second, but I'm sorry. You can reconstruct this computation. It's an easy computation. I just want to tell you that what I remember is that there is a solution. So it is actually an equation. So would G minus be the first order operator with respect to M2? There will be no problems at all. Because you may consider Q closed things, etc. However, it's a second order operator, and that's why okay, please believe me, and you may try to compute it. That if you introduce an operator H, that is homotopy, so H is homotopy in P4, okay? Homotopy of Q in Pi4. Then what I'm trying to say is that you can choose phi2 in the following way. If phi1 is both Q and G minus closed, so if it is in what I called QG cohomology, that is P1. So what you have to do, you just need to consider phi2 like this. You see, maybe we can make this computation, but unfortunately, right now I'm a bit tired. It's written in my paper with Shadley. So phi2 should be like this, and there are also higher phis, like phi3. So if we took this, exactly this phi2, then phi3 has the following representation. And also G minus. So this is a solution to homological Todorov. This is homological Todorov theorem. So phi k, so phi is a sum over trees. So here you have this hg minus, it's a product. And here we have this h. So, by the way, hg minus is equivalent to divide by z in some sense. Okay, so in this way, you solve this problem. And this is a constructive way. I'm sorry for being tired and stupid, you see, I cannot properly think. So I cannot properly make this computation. But it's true.
But it's okay. I saw the similar diagram in your paper and also in the original paper of PCUV. So it's a kind of a bit familiar.
Okay, so here is this h. So you see, at some moment you are so tired that you cannot make computations, but still some other piece of my brain that knows the knowledge is active, you see.
I see. So
I'm telling the truth, being not able to perform simplest tree computation. Okay.
I understand. So it's 1 hour and a half past. So
but still I want to come to the point.
Okay.
So the point is that not only you have a solution, you have a special solution. And this solution is parameterized by phi 1. Okay? Now having this solution, you may plug this solution to the formulas of induction of the M1 structure on cohomology. Let us call this solution T, okay, due to Todorov. So we are coming to this formulas. And I'd like to discuss this type of formulas. For any solution to homological Torelli problem, we have a commutativity equation. However, now we take not some solution, but Todorov solution. It's good to mention a person. So having Todorov solution, we have a special solution to commutativity because we start not with some homological bicomplex, but with Todorov homological bicomplex. So now let us see why Todorov, how Todorov solution to commutativity is better or is distinguished among other solutions. It's because it has extra symmetry. Actually, there is phi 1 standing here in commutativity. And there are phi 1 in Todorov operator. And this Todorov solution is special because things are symmetric. You can easily exchange this phi 1 with phi 1 that stands here. Because this result would be the sum So what I wrote here, first there is an equality. It means that there are two sides, left-hand side and right-hand side. In the right-hand side, I drew a graph. I drew a tree. That is BCOV tree. Or you may call it Hodge string at the tree level. As a propagator, you have homotopy times G minus. As a vertex, you have multiplication. As a leaf, you have phi 1. There is no cyclicity, but I don't need it at the moment. Let us omit cyclicity for a moment. On the left-hand side, I have the induction of the bicomplex. With the Todorov element. But you may see term by term that they are the same.
So the Todorov solutions have this. Todorov solution is a series with respect to the variable t, I guess, right?
Yes, but you may expand it. So in Todorov, you may consider Todorov solution as something non-linear in phi 1.
Yes, yes, and the one of the term maybe corresponds to the this tree where 4 leaves corresponds to the right hand side.
So when I write this, I say consider the sum. So here I have the sum of these types. Okay. And here I have the sum of over trees. You might see that terms look similar. Okay.
Mhm.
You just need to see that they are exactly the same.
Mhm.
And explanation is easy. Suppose you have a tree, any trivalent tree. Pick up, so oriented tree. Pick up a leaf, arbitrarily pick up a leaf.
Mm.
Then we can draw a unique path on the tree connecting leaf to root.
Mm.
Okay? And then you can see this curve or line. And these are branches. Okay? So that's how you combinatorically can decompose a tree as a line with trees coming in.
Mm.
But then you see that this exactly brings you description in terms of Todorov elements. Because contribution to these trees, contribution how these trees are coming in is exactly through Todorov elements. That's why Todorov elements give a special parameterization of solutions to oriented WDW. By Todorov, of course, I mean homological Todorov. So it is just decomposition of the way to whenever you decompose a tree as I forgot this English word. Okay, as a line with branches,
But
you get this.
but so when you're considering the oriented tree, usually there are
Oriented.
a single root, but you have many choices of leaves.
Yes. Uh, uh, equivalent.
Yes, of course.
Yes. So you choose this leaf.
Mhm.
You have this, let me call it core.
Yeah.
You have core with branches. This tree will have decomposition in terms of core and branches. If you choose as a distinguished another leaf, you will have another decomposition of the same answer as tree with branches,
Mm.
as core with branches. And you have an extra symmetry. You can choose any leaf as a distinguished leaf.
So having a Todorov solution somehow gives you a special parameterizations of
Yes, exactly. That's why Todorov solution gives me a special parameterization. So it first of all, it gives me special parameterization of solution of Torelli problem.
yes.
Moreover, this parameterization is distinguished because if you add it in the formula of homological bicomplex, you will get symmetry between elements here and inside Todorov, like here. And that's why commutativity equation would turn into oriented WDVV.
So if you go back to my original question, so my original question was something like, when you want to have this oriented WDVV, it seems like we have to identify these two different colored mark points on Losseff-Manin space. So I think the white input and outputs are on the two ends of the graph on the left-hand side. Is that right?
So what? So black points correspond to operators.
Operators.
White points correspond to states or elements of the vector space.
So choosing a Todorov solution somehow gives you an identification between these.
Yes.
Points.
Yes, and you see how it works in this particular example.
So I always thought those kind of identification is some sort of a metric in Frobenius structure.
Metric?
Yes. Is that,
It has nothing to do with the metric.
okay, so they're different things. It's just an identification.
So you see, so it happens that there is an oriented version of almost everything here at the tree level, and people for some reason are mixing them up, and even Kyoji Saita is mixing this. So when Kyoji Saita formulates his theory, he imposes extra condition on the good section, such that the resulting structure would be orthogonal with respect to this metric. But for the purpose of oriented associativity, it's not needed. And this confuses things. You see, if you have two phenomena together, it's hard to understand what's going on. What I'm trying to do, I'm decomposing things into pieces. So in particular, I gave you decomposition, okay, two decompositions. First, it's possible to take metric aside.
Okay.
When we go to oriented. In the oriented world, it's possible to treat things separately. It's possible to take the clear picture of induced bicomplex, this picture. Okay? Because when you work with differentials, you don't have multiplication. Differential is a unitary, it's binary unitary. Okay, one-to-one, so it's linear operator. One input, one output. How should we call it? Not unitary. Okay, it's unfortunately. So binary and okay, one input, one output operation.
Okay.
Okay, I'm starting to forget what. Okay, so you don't have a room for trees.
Oh.
The only thing that you can have is this.
Okay, so in a geometric way, so the one of the special properties of the Todorov solution is they are all G naught minus closed, right? The components are G naught minus closed.
Yes, but of course phi one is G is G minus closed.
And
but Todorov solution is, you see, when I told you Todorov solution, it's clear that it's just one of the solutions. There are other solutions. Would you have other solutions to homological Torelli? You would not have this symmetry.
Oh,
Todorov solution is preferred in such a way that when put inside the homological bicomplex formula, it gives the formula that is symmetric with respect to phi 1 enters here and here. That's why Todorov element is very special. I told you that it's not just a solution to homological Torelli. It's a preferred solution. It's a very preferred solution to homological Torelli. And for some reason, people don't even stress it. People used to formulate Todorov theorem as the theorem that there is no abstraction. So if you hear how people are presenting Todorov theorem, they say, due to Todorov theorem, there is no abstraction. But it's only one half of information. Not only there is no abstraction, there is a Todorov element that has explicit form. It's a preferred element, Todorov element. And if you use Todorov element into bicomplex, you will have this miraculous symmetry between the two types of inputs. And this is what is behind the special coordinates. In particular, if you try to work it out with Kyoji-Saito theory, you would be surprised, because the Torelli equation is empty. You may ask, how can you get special coordinates? So you get it by considering Kyoji-Saito theory as the generation of the Hodge and all this blah, blah, blah. But you need to understand that that the trick here is the Todorov element. I was sorry for not stressing it from the very beginning. Todorov element is a distinguished element. Todorov theorem has two parts. First, no abstraction. Second, there is a distinguished solution. And you know, it always happens in mathematics. If you invent something great, you typically invent it as a lemma. And people think that it is a lemma to prove something. But later on, it turns out that your lemma is actually a new construction with a special properties. And you say, no, it's not a lemma. It's a something. So nobody uses the whole Todorov element. Okay? I use it because it's distinguished. And unfortunately, when we wrote a paper with Shadrin, we did not stress it. We understood it. It was also in our proof. But it is buried inside, you see. This statement, that statement, we had to underline this. So several years after, we wrote a paper with Shadrin. Actually, we wrote a paper of genus 1, on genus 1. So we considered genus 0 as a warm-up case. So you could not find the stress on Todorov element there. We use it. We use it in the proof. But we were not stressing the importance of it. Okay? While it is this Todorov element that is a key to understanding of what special coordinates are.
So the things are going other way around. I thought the commutativity equation comes out first, and WDVV, it's kind of...
Yes, but it's like this. So commutativity equation is the homological bicomplex equation.
So actually the WDVV, the sum over three things coming out, even though we don't have this G minus, right? But if you have this G minus extra structure, then you can pick up this special solutions, then it gives you this
Exactly.
special things.
You see, in this construction, you see, when you say what comes first, what comes second, it depends on what you are doing. So what I explained to you is the particular case. It's the Hodge string point of view.
Okay.
With a very special, I'm sorry, with a very special property. It's not the most general property, but if you have a Hodge condition, then you have what you have. Then you have WDVV, then you have distinguished parameterization, etc. If you will relax Hodge condition, I would say in the spirit of Kharoshkin, Shadrin, Kharoshkin, Markaryan, Shadrin. So it's possible to relax Hodge condition. Then you will have more freedom, and then you'll see that there is an ambiguity in choosing special coordinates. You see? But before I wanted to discuss the ambiguity in special coordinates, I thought that it is worthwhile to discuss case where they are unique and natural. So once again, the commutativity equation is invariant under diffeomorphisms of the base. The WDVV is not. So in Hodge string construction, WDVV comes as commutativity with the Todorov element.
Okay. So
And that's why I spent some time on explanation of the Todorov element and why it's important. Okay, so I should call, so now I see that I should call this talk Hodge string construction and Todorov element, but
so I think this would answer my I think that was the first or second question, I think.
no, it answers the first half of your first question, because I have more to say on this.
Okay.
Because, but unfortunately not today, because I have to restrict myself. You see, I am a bit tired, so it's hard for me to make a simple graph computation.
But that's fine for me, because
you see, so I have to. That's why I'm trying to pass my understanding. You see. You see, when you are so tired that you cannot even compute, there is still something that is in you. It is the understanding of what is going on.
It's fine for me. I think
I wanted just to pass to you this understanding, this piece of understanding. And next time I'll tell you more.
Okay.
Namely, you see, namely, we will discuss d tau dt equation.
Is that T a Taylor thing? Taylor solution?
No, so this, okay, d tau AB dtB equals to 0.
Oh,
This is the special coordinates equation.
yeah. Hmm.
And it's interesting to study space of solutions and compare it with the space of deformations. Space of solutions to commutativity equation. There are similarity, and this space of solution and this space of solution, and there is also a given time group.
Oh yeah, for sure. Yes, yes.
Acting here. So if you write it this way, you will see the full given time group. And it's exactly the place where I owed a bottle of beer to Robert Dijkgraaf.
Mm.
When I was talking on this in Netherlands, I wanted the students to be more active during the talk. And I asked them to solve the first order deformation problem to this real time. Just I stopped my talk and told that I'll give a bottle of beer to a person who can solve it in 3 minutes. How to solve this? So suppose we have this solution deformation plus A. Solve it. Solve for A. I wanted students to be active, and I said that I promise a bottle of beer to a student who would solve it, because they like beer in Netherlands, in Holland. So students were shocked because nobody was proposing problems during the talk. After 2 minutes, Robert Dijkgraaf found the solution. So I have to buy him a bottle of beer. But you know, his position is that high. So I hesitated to buy him a bottle of beer. So I have to buy him a bottle of beer. So you see, it's funny that these equations could be nicely studied term by term in perturbation theory. It's possible to guess the solution, and then you may get from this dressing transformation and integrable structures. So in this way, you see, I answered to 1/2 of your first question, and next time, when I hope I'll be more energetic, I'll answer to the second half of your first question and the first half of your second question about integrable structures, about dressing transformations, etc.
Okay.
Because I had a paper, but I was shy to publish it on the archive. You know, I don't know why, but where I discussed this, and it was Volodya Fok who helped me in dressing transformation, because I don't like integrable systems.
Okay, so I think it's a good point to stop. So I'll stop my recording.